Good.
Good. Did you guys have school today?
Yeah, sadly.
I'll bet you when you woke up you were looking for that cancellation.
Oh, yeah.
There was a lot of cancellations, but not Jefferson County apparently.
Nope, not a single Jefferson County was delayed or canceled.
Uh-huh. Okay, so this first problem, this earthquake problem here.
Yeah.
All right, I just got this, so I haven't had a chance to read it. Let me take a look at it. All right. This is an interesting question. I've always wondered about this because I always thought that every point on the Richter scale was 10 times. In other words, an 8.0 was 10 times more severe than a 7.0. But I don't think it's quite like that. Here, let's see if we can come up with an equation here. So they're asking how much bigger is a 9.2 than a 7.6?
Yeah.
All right. If it's a log base 10 scale, then the log of, we'll call it x, the severity of the earthquake, is equal to 7.6 in one case, and in the other, the log of that severity is 9.2. And we want to figure out how much bigger y is over x. Does that sound right?
Yeah.
Okay. Well, what's x equal to?
Wouldn't x be equal to 7.6 to the 10?
The opposite. In other words, the way I memorize this in terms of translating between logarithmic and exponential is I take the number on the far left, raise it to the power of the number on the far right, and that's equal to the number in the middle. So 10 to the 7.6 power is x, and 10 to the 9.2 power is y. So we have 10 to the 9.2 divided by 10 to the 7.6. Hold on, let me look at the question. How many times more severe? So what would that answer be? What's 10 to the 9.2 divided by 10 to the 7.6?
Would it... Should I do it on a calculator?
No,
or
subtract the exponents. You got a common base.
Oh yeah, so just 1.2.
1.6.
Oh yeah, 1.6.
So 10 to the 1.6 power, which is what? Go ahead and do that on a calculator. 10 squared is 100. 10 to the 1 is 10. So it's somewhere in between 10 and 100.
Yeah, it's like 39.81.
That should be the answer. It's 39.81 times as strong. Now, it's been a while since I've done these Richter scale problems with logarithms, so I think I did it correctly. I can't imagine a different way to do it. Let's think for a moment. Could it be the log of 7.6 equals x and the log of 9.2 equals y? Let's see. That would mean no. This is the way to do it. This is the way to do it. In other words, doing it the way we did it, if I had a 7-point earthquake and an 8-point earthquake, then I would have 10 to the 8th divided by 10 to the 7th, which would be 10. So an 8-point earthquake is exactly 10 times bigger than a 7-point earthquake. But a 9-point earthquake is 100 times bigger. It's 10 times 10. So the fact that this is 1.6 bigger on the Richter scale, 39.81, sounds very reasonable. So I'm pretty sure that's the way to do it. Let's look at B. So they want something that's 5 times bigger than a 7.6, right?
Yeah.
Okay, so we need a numerator there. In other words, I want 10 to the z divided by 10 to the 7.6 equals 5.
All right.
Okay. Now, how do we solve that problem? Well, hold on. My TV just went off. Let me go turn it down. So it's going to be less than 8.6 for sure, right? Because 8.6 would be 10 times bigger. So let's solve this equation. We got 10 to the z is equal to 5 times 10 to the 7.6.
Okay.
Now, how do we solve for z here?
Would be log z equals 5 times 10 to 7.6.
Well, we could take the log of both sides. Let's see what happens if we do that. If we take the common log of both sides, that is the log base 10 of both sides, it leaves z on the left, and it leaves 7.6 times the common log of 5 times 10. Hold on a moment. What's your calculator say the common log of 50 is?
$1.698.
What's that times 7.6?
$12.844.
Okay, so that's not right. Oh, why am I having trouble solving this right here? Why is that? Let's see. If I take that back over to there, instead of moving it there, and now 10 to the z divided by 10 to the 7.6 is 10 to the z minus 7.6, and that's what has to equal 5. Now, if I take the common log of both sides, I get z minus 7.6 equals the common log of 5. What's the common log of 5?
Oh, wait. .69.
All right, there's our answer. I add 7.6 to both sides, and we get z is equal to 8.29. And that is a ballpark test also. It passes the ballpark test. Because like I said, if it was an 8.6, it would be 10 times bigger. So to be 5 times bigger, it needs to be somewhere between 7.6 and 8.6. So we did it right. Hold on a second. Just why did that give me troubles? I'm not sure why. I just didn't go about solving it correctly the first time. This answer feels right to me. All right, let's see.
That's actually all I had.
Really?
Yeah, because I have a whole paper, but that stuff he didn't explain correctly. Like, it doesn't make sense to me how he explained
Stat stuff. What kind of stat stuff?
That stuff, like the Richter stuff.
This stuff here, yeah.
It didn't actually explain it.
Well, yeah, it's not something I run across that often. This is probably only the second time in 5 years that I've gotten a problem like this. But the real key is knowing what the Richter, in other words, it's common log of R, or no, it's the common log of the severity equals the Richter number. That's what you need to know about earthquakes. So if one earthquake is a 7 and the other earthquake is an 8, then the severity is 10 times bigger. You see why? In other words, if I took the log base 10 of the severity of the 7, well, that's a 7. And if I took the log base 10 of the severity of 8, that's an 8. Well, in this case, if I translate it to exponential, I get 10 to the 7th equals its severity. In this case, I get 10 to the 8th equals the severity of the 8th. And if you divide the severity of the 8th by the severity of the 7th, you get 10. 10 to the 8th divided by 10 to the 7th is 10 to the 1, or 10. So every point on a Richter scale is 10. And if you remember that fact, then you should be able to get back to this equation pretty easily. Okay? You know, I couldn't think of whether the severity belonged on the right side of the equal sign and the R may be here, but I'm no longer in doubt with that. This makes perfect sense this way.
All right.
So, in other words, a 9 compared to a 7 is 100 times more severe. A 10 compared to a 7 would be 1,000 times more severe.
All right. Makes sense.
And of course, replacing these with decimals instead of whole numbers, like the 7.6, that just means 10 to the 7.6th power is the severity of that earthquake. And you cannot measure the severity by the number of people that were killed or homeless or any of that. The measurement of the severity is merely the amount of energy that's released. And the damage that an earthquake causes isn't strictly based on the energy. It's based on how, like if it's in the ocean and it's vertical release of energy, it creates a massive tidal wave and can kill a lot more people. But in terms of just pure energy, that is measured by the Richter scale measurement. All right. Curious, what's this carbon dating problem? Is that one you don't have to do, or?
No, we do, but it's a really large problem. Do you want me to send you a picture of it?
Yeah, go ahead. We'll take a quick look at it here, and I'll see if I can't help.
Okay. Let's see.
Carbon dating problems have to do with decay. Which is logarithmic or exponential in nature also.
Come on.
Still looking at question B. There was actually two parts to that. We gave what its Richter value would be, and then it says, is this 5 times the R value of the Indian-Pakistani earthquake? And of course the answer was no. In other words, one was 7.6, the other was like 8.2. So it's not. Answer to B is no.
Come on. All right, I just.
Okay. You send those to my David Cowan, 1949?
Yeah.
Okay.
Yeah.
Because sometimes I've had people send them to my other email address, and that has to get forwarded, and it can take like a half an hour to get forwarded. This one's not coming in yet. These problems you got today in class? Well, Mitch, when are you taking your ACT?
Yeah.
Mitch, when are you taking your ACT test?
That's not till next.
So you're not going to take that this spring?
I'm only a next year.
You're a sophomore?
No, because I'm only a
Sophomore, okay. Because when you come up on that, make sure you work with me on that.
Yeah,
I can help a lot on that. But I am not getting this email. I don't know why. And I was just going to say that if you ever have a tutoring session scheduled and you don't have anything to work on, we can always work on standard ACT stuff or SAT stuff. And you can't almost begin that too soon. That's an excellent, excellent basis for just your standard math skills. Well, Mitch, I'm not getting this. I don't know why. Is it in your sent mail?
Yeah.
And you added the 1949? David Count 1949?
Yeah, because it automatically shows up. So.
Right. Yeah, and I got your previous one, which was sent at 3:59. I don't know why we didn't get this one. But you can see it's not coming through.
Yeah, it's weird.
Why don't you read the problem?
So, carbon-14 is an isotope of carbon that is formed when radiation from the sun strikes ordinary carbon dioxide in the atmosphere. Plants, such as trees, contain small amounts of carbon-14 because these plants take in carbon dioxide from the atmosphere. And then, yeah.
Okay.
The formula for decay of carbon-14 in the tree is given by A equals 10, and then raised to negative 0.00005 t. 4 zeros. T.
There's no E in this?
No.
Then 10 to that power?
Then where? Yeah. Where A is the percentage of carbon-14 remaining in the tree that is T years old in a decimal form. And then...
Okay, so they must give you an A, and they want to know how old it is, right? Which would be T.
Yeah.
So what A do they?
No, they actually give you a T.
Okay.
And the T is 150.
Well, multiply 150 by that decimal. So we have A equals 10 to the minus, let's see, 100 would move it over to that. It must be
0.0075.
Yes. And what's your calculator give you for that?
.98.
So they're saying that in 150 years, the percentage of carbon-14 will be 98% of what it was 150 years ago. Right? Is T in years, or is it in hundreds of years, or thousands of years, or does it say?
I think it's just 100 years.
It's in hundreds of years?
No, I think it's just 150 years.
Okay, so T is in years. Okay. And they're saying what is the amount after when T is 150. And there is undoubtedly a second part to that question, which is how long does it take until it gets to be 90% or some other number? Right or not?
Not in that question, but in the later questions there.
Okay. As long as you have the basic formula, and that's correct, there's only two variables in that. There's A and there's T. Okay? So if they give you T, you can certainly solve for A. And if they give you A, do you know how to solve for T?
Wouldn't it just be a log
Yeah,
question?
in other words, let's just do an example. Let's see how long it takes for the carbon-14 to get to be 90%. So how do I solve this exponential equation for T?
You would take the log, the common log of both sides, wouldn't you?
Okay, so I got the common log of 0.9 equals negative 0.00005t. So t is equal to that. And remember that if you take the logs of numbers less than 1, you get negative answers. So this log of 0.9 is going to be a negative number, which is going to make t a positive number, which it better be. You don't want to be coming out with any, if you come up with a negative t, you've made a mistake.
Okay.
So whatever that number is would be how many years it would take. Hopefully that number is greater than 150, otherwise we've made a mistake also. But I don't think it is going to be greater than 150. Good to go, Mitch?
Yep. Yeah.
I will talk to you next Monday.
Actually, can we do one on Thursday?
Yeah, next week or this week?
This week, because I have a test on Friday.
Okay. You want one at 4 o'clock on Thursday?
Let me check.
That's Thursday the 26th, right?
Yeah, that would work, yeah.
You got it. For a half hour, I'll see you then.
All right.
Bye-bye.
Bye.